All right, hello, my name is Alex Bongiovanni. I'm from Kent State University. I'm going to talk for a couple of minutes about representations of large integers as the sum of fractional powers of primes and squares. So first, the question is, can every natural number be written as the sum of a prime and a perfect square? And the answer is no. You got 34 is a small number example. There's just not enough perfect squares compared to the number of primes at that point. So okay, maybe small numbers are out. What about large numbers? And the answer is also no, because if we take a perfect square n squared such that 2n minus 1 is not prime, we get a factorization for the prime that forces our choice of the perfect square in the representation. And as long as 2n minus 1 is not prime, you don't get a representation that you'll get a contradiction. You have a prime equal to something which is not prime. So also no for large numbers, because we have some problems with perfect squares. But outside of that, it's conjectured that there shouldn't be any problems. So in 1923, Hardy and Littlewood conjectured that every large integer is either a square or is the sum of a prime and a square. And they also made a conjecture about the number of such representations for large integers. And so in 1937, Davenport and Heilbronn proved that this is true for almost all large integers, up to some exceptional set. And since then, there have been some improvements about the size of that exceptional set, and some work about when does this asymptotic formula for the number of representations hold. But the conjecture is still essentially open. And there's since then, not like any significant progress besides just knowing that the conjecture holds, except for some exceptional sets which are smaller than the number of integers up to n, but still quite large. So what's the Piaczewski-Shapiro sequence? We'll hit pause on conjecture H for a second. It's a sequence where you look at integers to real number exponents. So you take an integer to some real power. You get a number with a lot of decimal places, and you just throw away all those decimal places by taking the greatest integer function of that. So they're named for Piaczewski-Shapiro, kind of obviously, who proved a prime number theorem for them in 1953 that if C is between 1 and 12/11ths, the number of primes in the sequence matches the expected amount. And this is the kind of result that you get when working with these sequences, is you get some range of C, which is unfortunately usually quite short. But for this range, your result holds, and then outside of that, because the error terms involved depend on C, it's usually the result does not hold. And so we're going to use these sequences to approximate to conjecture H and see how far, in some sense, how far away are we from proving that conjecture. And throughout, we'll write gamma is instead of 1 over C, and just to simplify some of the exponents that will show up. So the first question is for what values of C can we write large integers as the sum of a prime and a fractional power? And the answer is for C between 1 and 69/62, and numbers that are large enough, you can always represent a large integer as the sum of a prime and a fractional power. And note, we don't say anything about squares here because when we're dealing with the greatest integer function here, we don't have problems with the factorization with the prime anymore. So we don't have to say anything about squares. 69/62 is still pretty far away from the conjectured exponent of 2, unfortunately. So the second question is, well, okay, instead of thinking about the prime plus a fractional power, what about a fractional power of a prime plus a square? And if doing sort of the corresponding idea of thinking about, well, what about when the exponent is less than 1? It turns out in that case, it's basically the same question as about primes and short intervals. So asking about C less than 1 is maybe not very interesting because it's the same as the question about prime and short intervals. So instead, we can try and extend the current results for conjecture H, which is that it's true for almost all integers, by showing that for C between 1 and 419/352, almost all large integers can be expressed as the sum of a fractional power and a perfect square. So we're kind of extending the work of Davenport and Heilbronn and showing that the conjecture, like some sort of extended form of the conjecture, is true for almost all large integers. So I'll go through sort of just a sketch of the proofs for both of these theorems. They're both mostly exponential sum estimation. Theorem 2 has some other setup involved with it, but For theorem 1, the setup is sort of the standard way of approaching problems like this, or I guess not the standard way necessarily, but a standard way, which is that if you have some equality involving the greatest integer function, you can rewrite that as an inequality. And in this case, there will be an integer solution to this, provided that there's an integer in between these two numbers and the gap between them is less than 1. So if we have a sum with some condition, like if we consider a sum over the numbers in some range, and we want to know if we have for a fixed large integer n, we're like trying to count the number of representations, we can detect this condition that n can be written as a prime power, a weighted sum over prime powers, and a fractional power. This condition can be detected with this expression here. And of course, the greatest integer function is difficult to work with, so we separate into just the number and the fractional part and deal with those separately. So we break the sum into two pieces. And this first part pretty quickly has order n to the gamma, so it's just mean value theorem and prime number theorem. So we just have to show that the second sum is pretty small. And in that case, we have this sum over rounding error. We have like a rounding error sum. We break it into two parts. You don't really care about the plus 1, doesn't matter too much. So we'll just deal with the second expression here, and we can use an expansion for the rounding error to get that our sum S2 is bounded by this exponential sum here. We still have the von Mangel function there, so using the generalized von identity, we can break this into lots of little sums with lots of variables, and then group those lots of variables into just two variables x and y, and work on cases depending if the resulting sums are type 1 or type 2. So we have lots of little variables here, and we group them into x and y, and then we have these potentially unsmooth weights f and g, which are like weighted divisor sums of these different weights here. So for type 2 sums, it's just single variable exponent pairs. Use Cauchy-Schwarz and the A step, and then several other B step and more A steps and things. Eventually you get some upper bound for the sum, which depends on y. And since our goal is to show that this is at most n gamma, this gives us a condition for the upper bound for y, that how large y can be that this method will give an acceptable size for the sum. And the A steps induce some sort of lower bound on y as well. So we get a range for the parameter y in which the sum has acceptable size. And nothing really depends on y at all, so we can do the same thing in x, and we get then together some range for x and y. And this all assumes that our weights f and g are not smooth. So now that we have some range for the parameters x and y, where we know the sum is of acceptable size, we can force if we choose a range for gamma correctly, we can force the parameters in the remaining case, one of the weights to be smooth, which is basically we have to choose gamma to satisfy some inequality. The 62 over 69 does appear here, but it actually could probably be removed, but it does appear again later, so we'll work with the stronger but potentially weaker thing. Sorry, the weaker but potentially simpler thing. And then you get several cases for the type 1 sums, but ultimately, if you check the exponents on them after using either a simple exponent pair, 1/2, or potentially multivariable b step, you get that the sum has size, the desired small size, provided that gamma is at least 62 over 69, gamma is 1 over c, so c is less than 69 over 62. So again, the bound appears here as well. It's probably not the most optimal result. Doing something more elaborate for the type 1 sums, or maybe breaking into more cases or something, could give you something better. But at least it seems like this is, if not the most optimal result, probably not at least terribly far from how good you can do, even with more cases. So for theorem 2, just to remind you, our goal is to show that almost all large integers are the fractional power of a prime plus a square. And we're going to follow the work of Balanzario, Greb, and Zoua, who's, I'm terribly sorry if I just butchered their names. I've only ever read them and never heard them. And we're going to work with this lemma. We're going to use lemma 3, which is pretty well known. And it tells us that if we have a weight function, which is 1, at least on some small range around 0, and 0 otherwise. It has an expansion as an integral, and so we can use this to transform a sum into an integral with certain properties depending on the parameters that we get to choose. So we make some choices about our parameters, which we'll come back to in a minute. And then based on our choices, we have that this expression here will be within the range that our weight function little phi is non-zero. Implies that a number n can be written as a fractional power plus a square. And the reason why we would want this is that if we consider a sum where we're looking at the numbers in between n and say 2n, and we want to look at the numbers that don't have a representation as a fractional power of a prime plus a square. If we use our function little phi here, because little phi will be non-zero only when such numbers do have a representation, this sum will only count or only get a contribution from prime powers because we're summing over the exceptional numbers. So we're trying to detect the exceptional numbers here essentially. So if we define S1, S2, and E as being, well, the pieces of the previous sum but with exponentials now, then our goal basically is to take our previous upper bound and use that lemma to convert the sum into an integral, and then we'll have these sums appearing in that integral. And our goal is to get a lower bound on that integral that somehow involves the size E, which is the size of our exceptional set of numbers. And then we can get some sort of bound on the size of the exceptional set, which should hopefully be less than n. So we can assume that the exceptional set has size at least n over log n, because otherwise we don't have anything to show. And in fact, we'll get a contradiction from this, as it turns out. So our goal is to take that upper bound and combine it with some lower bound that involves the size of the exceptional set. And so taking that lemma, we can rewrite the sum as an integral and then break up the integral into lots of pieces and treat each piece of the integral separately. So first is I0, is this piece of the integral where the variable of integration is near to 0. It produces our main term, and what we do is we take our sum S2, which is the exponential sum where the parameter is m squared, or the variable is m squared in the exponential. We can use the inversion formula to get a sum of integrals, but since alpha is so close to 0, there's just one term in that sum. And we can take that and then insert that into the integral near 0 and extend that to infinity. And now we have a new integral which we can apply the lemma to again in the other direction and build a sum this time. So taking our integral and building a sum in the other direction, we have that this our integral I0 is bounded below by this sum, which has order n to the gamma minus 1/2 times the size of the exceptional set, which is exactly what we were hoping, is to have some lower bound that involves the size of the exceptional set. So taking that and comparing it to the upper bound we got earlier, which was gamma over 2 plus 1/2, we get that is provided the other pieces of the integral are small, then we get that the exceptional set has a size which is at most n to the 1 minus gamma over 2, which is a contradiction to the fact that we assumed it was at least n over log n. And so far, no conditions on gamma, right? Our goal is to get some, or maybe not our goal, but ultimately we expect to get some conditions on gamma, which is to say conditions on C that restrict the range for which our result holds. And we don't have anything yet. Then I1 and I3 are actually quite quick to treat. I1 is pretty short, and so its size can be controlled mostly due to the fact that it's a relatively short integral. It's away from 0, so we do get some cancellation in the exponential sums now, and it has relatively small size. On the other hand, I3 is pretty small because our variable of integration is very far away from 0, and our weight function large phi has size at most 1 over alpha to the s plus 1, and s is one of the parameters that we get to choose in the lemma that allows us to do this setup. And as long as we choose it kind of correctly, we can actually make this the resulting exponent after we integrate. Even if treating these sums trivially, the resulting exponent can be made extremely small. So in this case, we can make the resulting exponent like almost minus 10, basically. So it's very, very small. It's a big O of 1. And the last integral is I2, is the difficult one to treat. So in this case, we actually split off a factor of S1 and treat that differently with just exponential sum estimation versus the integral estimation. And S1 is the exponential sum that contains the von Mann-Gelt function. So in this case, we treat the integral part just using Holder's inequality and some basic inequalities that are easy to establish for these integrals over these sums. And we get some expression, and comparing that to the desired upper bound for this integral, along with using the fact that we're assuming the size of the exceptional set is almost n. All we have to do is show that this sum over the von Mann-Gelt function, this exponential sum, has size at most n to the 3 gamma minus 1 over 2. It's still, so far, no conditions on gamma. And what we do now is we basically play the same game as we did in theorem 1. We have some exponential sum that's weighted with something which detects prime powers. So we use Vaughn's identity and break the sum up into lots of pieces, and then recombine those pieces by combining the little variables that we get into variables x and y with some potentially unsmooth weights f and g, which are like divisor sums. And then we treat type 1 and type 2 sums separately. In this case, rather than doing single variable exponent pair stuff, we use a result from Baker and Weingartner, which is quite nice for double exponential sums, so we can just, it applies immediately. And using that, we get different error terms dominating depending on the size of C, so you have to check some cases and things, but essentially for most of the resulting ranges, almost, we can get type 1 sums, we can force type 1 sums to exist, and those are easy to bound even just using the pair 1/2, 1/2. So the type 1 sums end up being quite small. The only problem is the last range here that shows up, and in this case, forcing the type 1 sums to exist doesn't quite hold for the entire range down to 5/6. So actually 352 over 419 is somewhere in between 5/6 and 49 over 58. At the very beginning I had the number for it, so 419 over 352 is like 1.19 something, so it's almost 5/6. And again, this is not necessarily the most optimal result, so it seems like possibly doing some more cases or some sort of weaker condition trying to make the type 1 sums happen, you could possibly get down to 5/6 in this problem, but I didn't go that far. Well, obviously you can't ask questions in a video, but thank you, and that's it.